So welcome everybody, good afternoon. This is afternoon session of day 6 of the INO week, special INO week at the Vigyan Samagam exhibition of mega science projects. This session speaker is Professor Nabha Mandal. To introduce him to you will be a big task. Actually, he was in TIFR for nearly 4 decades. He retired 3 years back. He was the project director of India-based Newton Observatory INO since the inception. In fact, he and a few of his colleagues had this brainchild of setting up this premier Newtonophysics experiment in India. Basically, he's a particle physicist, high-energy particle physicist, and that too is an experimental physicist, one of the foremost of experimental physicists, if I can add. He has been in very large collaborations all his career. He did his PhD in the proton-decay experiment at KGF, then subsequently he was in the D0 experiment at Fermilab, then in CMS before he conceptualized this INO project, and he was the project director until his retirement. Right now he is the Raja Ramanna Fellow, and he is at Saha Institute of Nuclear Physics. He has been awarded the Bhatnagar Award, the J.C. Bose Award, and also the Third World Academy of Sciences Prize. So he is a well-decorated experimental particle physicist, and it's a real pleasure to hear him speak today. Professor Mandal. Yeah.
Introduction. So this afternoon I am just going to give you some idea what to do if you want to take up particle hunting as your profession, and how do you go about it, what are the arms and ammunitions that you need in this job. So now, before that, what do a particle physicist do? What do they do? What is the question they ask, and what is the type of answer they are looking for? So basically, if you see, the particle physicist, they want to answer two major questions. One is what everything is made out of. You just look around, it's like a child, you break things apart, and finally what it is made out of. What is the bricks and mortar that this whole universe is made out of? So what is the basic constituent of matter? Now, and then how do they all put together? How do these particles come together and combine and to form this complex elements that we see ourselves, and even chairs, tables, the sun, the stars, all those complex objects, how those basic constituents, from there we go there. So this is about the forces that control the behavior of particles. So for example, how do the protons and neutrons form the nucleus? How do the nucleus and the electrons form the atom? How the atoms combine to form the elements and molecules, and so on. So these are the basic questions we always ask. But this is not that we are asking it today. For many thousands of years, from the ancient time, the same questions are being asked again and again. And if you go back to the early history, then you will see in the ancient Greek or even in Indian philosophy that if you look at, they will say that the whole universe is made out of basically 5 elements, Panchabhuta. Those 5 elements are very simple. Whatever they could see around them, that's what they're made out of. The earth, air, fire, matter, and sky. That was everything is made out of. So it's simple. The whole universe is made out of 5 things. So you have to remember 5 things, and life is simple. But over the time, this has changed a lot. And by 1900, basically the chemists, through their alchemy, they were started looking for all the matters, and they have discovered something like 100 elements by that time. Okay? From hydrogen onwards, various elements they have discovered. And that was the time people thought that is the basic elements of matter. Okay? Iron, basically a block of iron is made out of iron atoms, and a block of silver is made out of silver atoms, and they sometimes combine and make complex elements. Okay? And so on. So that was also a nice picture, and that was the picture that you knew about 1900. But the first major discovery after that time came in precisely in 1911, when Lord Rutherford, he was bombarding using alpha particle, a plane of gold foil, and he found that atom, which you thought is the basic fundamental unit, is not anymore. It has a structure inside it. And they found that it is, and from there we got the ideas of protons and neutrons and electrons. Okay? So this is by 1936. Electron was discovered in 1897 by J.J. Thomson, if you remember. And then neutron came in 1935 around. So by the time 1936, again back to 3 elements, not even 5. Even life is much simpler. We only needed 3 elements, 3 particles: protons, neutrons, and electrons. Protons and neutrons makes the nucleus, and then electrons go around it, make the atoms. Make more protons and neutrons, you get heavier and heavier elements. Okay? But basically all the elements are made out of protons and neutrons, and electrons going around it. So even we are very happy that, okay, things are simple and how this universe is made out of. But just after that, particle physicists started doing experiment, and they were discovering one after another new particles, and became very complex again. By 1960, this is due to the advent of particle accelerator, where you can make artificial beam of particles and collide and then make new particles. We had almost a zoo of particles. Okay? Many new particles were discovered, and we actually, the Greek alphabets are getting over almost, naming them. So for example, these are the particles called pi 0, pi plus minus, charge pions, charge kaon, neutral kaon, eta meson, and it goes on. And this is their masses. Okay? Then similarly, proton, neutron, lambda, cascade, and sigma, and so on. Okay? Again here, omega, these are the particles. Similarly here, electron, muon, tau. So it became so difficult, so people started first to understand what is happening. You have to classify them first, see their properties. So they classify them here in the range of their masses. For example, if the particle mass was less than the proton mass, then they are putting into the class called mesons. Okay? These are actually the masses of those particles in some unit. Imagine that one, that proton is roughly around 1000, 938. Say proton is around 1000 MeV. So this is half the proton mass, this is less than half, and this is almost one fourth of the mass of the proton, and so on. So these are the masses. And see here, these particles are successively getting heavier than protons. Okay, their masses. Okay, their protons. These are actually very strange type of particles. These are the particles are completely different from this set of particles. For example, electron, muon, and tau, they are the set of particles are completely different than these particles. And many such particles are still getting discovered. Again, the idea of this became very complex. So then, are these all fundamental particles then? The question is there. I mean, we have seen those particles in cosmic rays and experiment, so these must be fundamental particles. But then, to really accept that there are so many fundamental particles is not there. I mean, it's just, that is hesitant in our minds to accept them as fundamental particles. Then came the looking into the particles again, all those particles putting into according their certain quantum numbers. For example, these particles has quantum number like charge. Charge is a quantum number. Some particle has +1 charge, some particle has -1 charge, some of them has even more, some of them have less. There is also some other quantum numbers like the particle, this charge here called strangeness. These are some quantum numbers, they are associated with these particles. So if you plot them as a function of strangeness and charge, then you can start looking into these particles can be put in some 8-fold way. Okay? This is the famous SU3 model of Gell-Mann. I am not going to that details, but same thing. See, these are all the baryons. You see, these particles. Here you are showing these particles are put into this multiplet. Similarly, these are the mesons. These particles are put in the same multiplet. Again, as a function of strangeness and their charge. Look, they are following exactly same pattern. Okay, similar pattern. This gives them the idea that maybe they are made out of something else. And they actually invented some new particles called quarks. Quarks was not seen by anybody. They invented this in 1964, and Gell-Mann and Zweig, two gentlemen, they said that, okay, let us say we have three quarks. They are called up, down, and strange. Okay? And they have these charge. This quark has charge 2/3, and these quarks have charge -1/3. Similarly, they have strangeness -1, 0. And the particles, every particle has to have their antiparticle. That Dirac has told us, every particle. So if they are particle, they are their antiparticle, U bar, D bar, and S bar. Okay? And they have their corresponding charge and strangeness. If you see the U has a charge of 2/3, then U bar has to have a, this is gone I think, U bar has to have a charge of -2/3. Can you have batteries on it? I think batteries have gone. Okay, so -2/3, and similarly these two has, no, anyway, go ahead. It is working sometimes, sometimes not working. Sorry. So you see their charge is -1/3. These are, their antiparticle has charge 1/3. Now you take this particle and then think that other particles, these K mesons and then neutron, proton, those multiplates, they are made out of these quarks and their antiparticles. For example, these are the combination. This one is a quark and an antiquark. Okay? Made out of the mesons, the lighter ones are made out of quark and antiquark. And this heavier one, the baryons, they are made out of 3 quarks. And if you put them properly, arrange them, they can explain all the particle and their properties. So that only as an idea. And when they wrote that paper, they told that this is only a theoretical exercise. These quarks may not exist, but if they exist, then they should nicely fit into the picture. But soon afterwards, experiment was done and they found the quarks exist. And that was really the turning point, and we thought that we got the final constituents of matter. So what were those constituents? So we think that as per today, the whole universe is made out of 6 quarks and 6 leptons. Okay? What are those quarks? Those up, down, and strange. These 3 were originally introduced by Gell-Mann in 1964, and 3 more we have discovered afterwards. Okay? And the latest one, the top quark, that is the D0 experiment he was talking about. The top quark is the latest one, but with these 6 quarks. And these are the 6 leptons, they are called. They are electron, muon, and tau, and the neutrinos. Okay? Corresponding neutrinos. Now, actually speaking, to explain everything, we don't even need all these particles. We only need up and down quark and the electron. Only these 2 and this. Because protons is made out of 2 up quark and 1 down quark. A neutron is made out of 2 down quark and 1 up quark. That's it. So once you make proton and neutron, you make all the elements and the nucleus. And the electrons, you put appropriate number of electrons rotating around it, you make all the atoms and so on. So you don't even need other particles. But for some reason, nature has given us as additional gift those particles, and we have to live with that. There are another properties. These particles, they are very unstable. Okay? They just decay to stable particles like this. So that's why these particles, you do not see them all the time. You can find a proton all the time, but you don't see these particles because the particles will decay to other particles. So you can't see them. So this is what all the particles are there. Now the question comes, with this structure, let's look into our matter. So if you can see matter at a level, if you have a microscope, and you can see up to 10 to the power minus 10 meter resolution. So 1/10 billionth of a meter. Okay? That is the size of the atom. So you can see the atom. If you can improve your resolution by another factor of 4, say 10 to the power minus 14 meter, if you can see up to that, then you will be able to see the tiny nucleus is a combination of protons and neutrons, tightly bound. Okay? Now, if you can further look into this protons and neutrons, then you can see the quarks inside them. And finally, even inside them, not only 3 quarks, there is a large number of virtual quarks and anti-quarks all the time getting created and destroyed. They are called virtual people. They are always there. And then you can ask the next question, that what inside the quark? What made out of this quark? And we have searched that in the latest experiment up to 10 to the power minus 18 meter resolution. And we have not found anything so far inside the quark. So once we have not found inside anything, so we call it structureless. So we think this is the ultimate building blocks, the quarks. But this is today's picture. Maybe tomorrow, a powerful accelerator, you can smash these quarks and you find something inside which is even smaller than 10 to the power minus 18 meter. And then you will see the new structure inside them. For example, the people like string theorists, they are talking at the level of 10 to the power minus 30 centimeter and so. So there are a long way to go, but this is, I am an experimentalist, I only talk what we see, and this is what we have seen so far. Okay, now, so this let us avoid. So one slide I will give you. So I am talking about this micro world, the smallest size. Why? But it has a deep connection with the whole universe, because the universe in the original time, when at the Big Bang, 13.7 billion years ago, the Big Bang started, and that time, the universe you see today was not like this. They are a dense, hot soup of those elementary particles at that time. So they are all these quarks and leptons and all those things are there. No matter that we see today, nothing else, no structure. Only these quarks and leptons. So by studying the quarks and leptons in our laboratory, we can discuss the early evolution of the universe. So this is the only way we can understand how the universe was there at the very early stage. So that is the deep connection between what we see in the small laboratory, in the tiniest particle, to the whole universe. So this is but then how do the particle physicists all, see, I have now so far, I have told you a story. These are the things, these are made out of that, but is it true? How do you get those information? Okay, that's really my talk. So for example, the particle physicists, how do they do experiment? We need 3 things for doing an experiment in particle physics. One is called an energetic beam of particles, and a target and a detector. So let me explain that by giving you this. Rutherford did that experiment in 1911, that's what I told you, where he found the structure inside the atom, the nuclear structure. How he did? So he had a source of radioactive elements. The radioactive elements always emits alpha rays and beta rays. So this guy was emitting alpha rays, energetic alpha rays, few MeV only, not too much energy, but few MeV. And he used that alpha rays, and then he has a gold foil, and he was hitting those gold foil, and then once you hit there, these particles get, go in different direction. And if the atom till that time was thought of a homogeneous object, there is no structure inside that. So it has only positive charge and negative charge inside. It is like a pump pudding model. It's like a cake. Inside that is the whole thing is made out some positive charge, and there inside some negative charge is there, and that's all. So if that is so, then you expect these particles to get scattered by a very small angle. They will scatter. However, in case what happens was there, you have the atomic structure, whole atom was almost empty. But there is only tiny nucleus which has all the mass of the atom. And if so, when the alpha particle hits that atom, at the nucleus, then it will get scattered by it's like one marble is hitting another marble. Usually you just throw a marble to another marble. If it doesn't touch, it will just go away. Nothing happen. But if it hits that the marble or if it's a bigger object, then it will get reflected by a large angle. And that's what they found. And that's what, so this is our energetic beam of particles. This is the target, and this is where you see your screen, where you can see where the particle is hitting. This is your detector. Now, the detector, so here what is giving a picture of a cosmic ray event. What has happened? We say that our Earth is getting bombarded all the time by cosmic rays. Is this just I am saying? But how do you prove that it is happening? So you take this film, like I want to take your picture. I have, in the old days, you have seen the black and white film. You know how it used to work? It has a deposit of silver bromide in the film, okay? And when the light falls, wherever it falls, it will ionize those silver, and then you develop that, and that will come as a black spot. Similarly, here also, this is exactly same thing called nuclear emulsion. Nuclear emulsion is a photographic plate. You just go to a mountain altitude and keep it there. And then few days back, you bring it back in your lab, and you expose them and see whether some particle is going through that. And sometimes you will see this kind of picture, as if something has happened here, and all these particles are getting direction of something. So this is what we call is the one particle has come and has interacted and produced all those particles. So new particles have been created. You can get the picture. Here, one cosmic ray particle is coming, and then it is producing many particles, and so many of them that you can see almost like a thick band there where many particles are going. These pictures are taken by such photographic emulsion techniques. So this is a technique you do. So then this is one thing, this is a detector. Then in the old days, we had free available of energetic particles. Rutherford time, the energetic particle was coming out from from the decay of radioactive elements. That was. But then soon he discovered that there are much higher energy particles available in the cosmic rays. Okay? In cosmic rays, we have higher energy particles. But then around 1940s, we actually found out how to create energetic particles. You take an ordinary proton, and then you can energize it to higher and higher energies. So it is like that, it is, if you have a marble here, it has zero kinetic energy, it is just living here. It is zero kinetic energy, I will say, right? No kinetic energy. But if I just go and hit that marble, then it will start moving. Why? Because it has a kinetic energy. Where from it got the kinetic energy? Because I give it a kick. So it got kinetic energy. So what we do, we take the particles also and give them kick, okay, and then energize them. Where do we energize them? In a particle accelerator. So in a particle accelerator, what happens is that these protons or electron, they are charged particles, first of all. So charged particle, if it moves in a magnetic field, it gets bent, because there is something called Lorentz force, and you can bend them. So for example, so these green things are magnet, and inside that the blue one is a vacuum tube inside which I have kept those protons and electrons. And now when the protons and electrons is moving in the tube, these are called bending magnets, they are keeping them in almost like a circle. Otherwise these particles will go straight, because the particle will go straight. If I throw this stone, if I don't bend it, it will go straight. But I don't want them to go to bend. I want them to stay inside the ring. So I put this magnet. They are called bending magnet because of that. And the blue thing is where the kicker. That is where, when the proton comes, I give a kick. How do I give a kick? Because if I keep a proper potential difference at that time, and then the potential difference is in the right direction, it will get energized. And this is how we create, and we energize it to higher and higher energies. Ultimately, at some time, we say that enough energy, now we can use it, and we use that particle to hit a target. So there are particles coming out of this accelerator and hit a target. And then while hitting that, it will create many new particles, and we study those particles. Now you can do it, you take this energetic particle, take out of this accelerator and hit a target. This is one way. There is another way. So this is like, if you have a collision, if you have a motor, if a car you are driving, and if you want to enjoy the impact of that car hitting a wall, you go and hit the wall. Don't do that, sorry. But you know the impact. But imagine that impact and compare it when two cars hit head on. Which one will be much more impact? When they hit head on. And we do exactly that to get even more energy. So that one, so you have a particle going this way and another bunch of particles going this way, and they hit head on, and that place you create new particles. Okay? This is called colliders, and this is the Large Hadron Colliders that is right now operating in CERN in Geneva, is exactly that kind of machine. A beam of proton going this way, beam of proton going this way, and hitting and creating new particles. Okay. Now, this creating new particle business is something like this. So you have a collision. Now, what do we collide? We collide a proton with a proton, or an electron with a positron, or something like that. Okay? But from the collision, we don't get proton all the time. We get new particles, a muon, a pi meson, a Higgs boson, a top quark. All those things can be produced. Imagine that, like a magic, that you are hitting two strawberries here. Okay? You are hitting two strawberries one to each other. But what you get out from that collision is all these other fruits, apples and bananas and so on. Exactly particle physics, we do that. Okay? And this is possible because of Einstein gave us this famous formula, E equal to mc square. In this collision, that energy that is available, you can convert that energy into the mass of the new particles. So you create new particles all the time. Okay? So this is how you create particles. Now, so then this is a Large Hadron Collider. I mean, how big? So for example, how big is the, so if you want to go higher and higher energy, you have to make this circle bigger and bigger. So we have gone so far. This is the biggest accelerator. This is 27 kilometers in circumference, and this is in 100 meters underground in Geneva, just outside Geneva. This is actually Switzerland, Geneva Lake, and in that we have set up this. So this is the below that 100 meter below. This is the tunnel, and this is the ring talking about. And all those blue things you are seeing, those are the bending magnet. And inside that, deep inside, there is a tube called vacuum tube through which the particles are getting accelerated. Okay. So we do experiment like that. Now, what we get from that collision?
Even under identical conditions, you get completely new particles.
Says that.
If I have two collisions, I do.
You don't know. So they are completely independent. One collision, you may get some particles. In the next collision, you get completely different set of particles.
Even if my starting conditions were same.
Absolutely, absolutely. So that's why not every collision you will get Higgs boson. You have to study many, billions collision. Maybe one of them is producing a Higgs boson. That's why it is so difficult. Okay. So now, what do you get from that picture? So ultimately, from that collision, you come out with those pictures, beautiful picture. Probably you have seen in those TV when Higgs boson was discovered. So can you come to your mind ever that how this picture was taken? Okay? I mean, here also at this moment in this room, a proton is coming and hitting and probably producing many other particles in this room. But we are not seeing them. Okay? But I am putting you this picture, beautiful picture of particles. And in fact, it is very clear to you that something is happening here, and all those ray-like things are coming out of this point. Exactly that's what happened. One proton beam has come from this side, one has come from this side, and they hit head-on at this point, and from their energies, all those particles are coming. They are of different kinds of particles. Their energies are different, their masses are different, their properties are different, but we picture them. And once we picture them, then we can analyze them and find out each of them what particle it is. Is this a new particle? And so on. That is how it. But the question is, how do we get this picture? So this is my particle hunter's guide. So how to look for particle tracks? Okay? So let's look at what are those particles, fundamental particles. So this is like I asked this question. So this is my favorite question, that you are Sherlock Holmes and you have come there for a crime scene, and some crime has taken place, and all the people who are involved in that crime has left in a car. So now Sherlock Holmes comes here and they look into inspect the road. And even Sherlock Holmes cannot find out anything, that whether really some car has gone in this road and so on. So he is scratching his head, and he realized that this is not a right place of crime. But if the crime scene has happened in a place like this, okay, now you can see the tire marks of that car. Not only that, from the tire marks you are smart enough, you will be able to find out which kind of car it is and how long back the car has moved out and so on. So you have to, when I say all the particles are going through right now, through your body, through this room, and that's because this medium is not prepared properly. The road has not been prepared properly to have left their mark. If you could have prepared the road, then you will be able to mark. So you have to remember, these particles are going, you have to just follow their footprints and find out trace their track. That's all you have to do. So, detecting particle. So elementary particles are extremely small in size, like protons, neutrons, electrons, all those particles. They're extremely small. We don't see them. Their sizes I showed you. 10 to the power minus 14 is the size of the nucleus. And some of the particles has no size. If it is a fundamental particle, it has no size at all. So you cannot be able to see it. Unlike normal matter around us, we do not see these particles. How do we know that this particle exists? Although invisible to our eyes, they leave behind their footprints. And you have to find out that. What is that footprint? The footprint is this. Whenever a charged particle is going through a medium, through the air, it is ionizing the air. Okay? Continuously it is ionizing the air. And what do ionize? So it is left behind this trace of positive ions and negative electrons. All the atoms in the medium is getting ionized. Only those which comes in its path, not far away. Only those which comes in its path. Now the particle just goes, just immediately it goes in the speed of light. But this ionization are there still for some time. If you leave it, they will start and combine themselves, recombine. But if before that, if you can collect those ions, then you will be able to see these tracks. So how do you collect or how do you do that one? So let's look into the early particle detectors, some of the detectors. So this is called cloud chamber. It was invented by C.T.R. Wilson in 1911, and he received Nobel Prize in 1931 for discovering cloud chamber. Then I'll come to that. Then photographic plates. I was talking about those photographic plates earlier. They are extensively used by Cecil Powell, and he received Nobel Prize for using those and discovering pi mesons. Bubble chamber, invented by Donald Glaser in 1951, and he received Nobel Prize in 1960 for this bubble chamber. Spark chamber, another kind of detector. So what are those? Like cloud chamber. Cloud chamber, this is the cloud chamber, this one, not this big one. This small one is the cloud chamber, where you create a supersaturated vapor. Okay? Supersaturated vapor, how do you keep? Suddenly, if you have some vapor here, and if you release the pressure, then it will become supersaturated. And so what is happened? If you have a vapor, then the vapor and the particle is going through that. When it is going, it will producing those electron ion pairs, and those ions becomes the nucleides for cloud formation. So along its path, particle's path, the clouds start forming along the track. So like this. So this is the cloud chamber picture, and this is the track. So these are nothing but clouds, actually, small droplets of clouds along the path. And this picture is very famous. This is the picture which is the discovery of the positron, antiparticle. This picture is a lot of things, because this is a positron going this way and stopped here. How do you know it is going this way? Because if it is not going this way, it is going this way, then it is electron. But if it is going this way, then it is positron. That you can see from the bending, which way it is bending, okay, when it is moving. So now, how do you know it is going this way? Look carefully. If you see there, the track thickness is smaller here, and slowly there is a lead plate. It lost some energy while going through the lead plate, and it is a lower energy positron. So it is when a particle becomes slower and slower, it deposits more and more energy. So that means it will create more and more clouds. So that's why its clouds become thicker here than here. And from that, they found out that it is a particle going this direction, and then from the curvature, it's not a E minus, but it has to be E plus. And that's why the positron, the first antiparticle, was discovered. So look at that. So imagine the importance of this simple device in finding out new particles. This is actually same cloud chamber picture, but what we have done, at the bottom of that one, we have kept a radioactive source. A radioactive source, if it is an alpha source, it is producing many alpha particles continuously, and each of them is producing a track. So you took a track of those in a nice dark room, in a cloud chamber, you will see all those tracks, millions of them. So that tells you how many particles, alpha particles, are coming out from that source every second or so, depending upon its strength. So this is a picture of that picture. Now this is actually another picture of electron. This is an energetic electron, much higher energy. So the electrons will go through a large distance. Here it is at almost 17 MeV initial energy. It starts with 17 MeV energy, and then I put it in a magnetic field. Again, magnetic field. Now you see it start going around, curling, and then it stopped. Okay? So the whole picture, one track, is going like that. How you do? You just have that cloud chamber, and you have to take a picture at the right moment. Okay? This is that. And these are some of these. These are cloud chamber. These are photographic emulsion. I told you the film. The same film you use for making your picture in the old days, not this your mobile picture these days, but in that one which you developed in the dark room. And so development is basically process. So these are these same plates, emulsion plates. These are, see, the photographic plates are nothing but there is a sodium bromide. Okay? Sodium bromide, and put in a solution there in a gel, and you put it there, and the sodiums, not sodium, the silver bromide, those silvers will get ionized, and then you just go because of the light, or because of going a particle. Same light, whatever a light will do, a particle will do. So here, what is happening, a particle is coming this way, and it decays here, produce a new particle, it is going up to that, and it is further decaying. This is a pi meson decaying to a mu meson, and mu meson decaying into electron. So this was the picture was taken by these photographic emulsions, and these are the picture of cosmic rays, those stars, what you call cosmic ray interaction. And this picture gave Cecil Powell his Nobel Prize, just this picture. And these are, this shows those photographic emulsion picture. This is a hydrogen ion, only it has one proton. This is a iron nucleus going. So you see, from hydrogen it has only one charge, and these are charge of 26. Okay, so this is, you see there, these tracks, photographic tracks, are getting thicker and thicker because they are producing more ionization. Because seeing, so from that picture, from the thickness, from the how much it gets scattered, etc., you will be able to find out what kind of particle has gone through. That's what I was telling you. Not only you will be able to know a particle has gone through, what particle has gone through, you will be able to find out. Now bubble chamber. Bubble chamber, see, cloud chamber, as I told you, is supersaturated vapor. A bubble chamber is a superheated liquid. Superheated liquid. So superheated liquid, you see that, you do that every day, actually you see those superheated liquid. You don't see them, but it is happening around you, in house, in your home these days. Everybody has a pressure cooker. So what is there inside the pressure cooker is superheated liquid. Okay? You don't do this one, but if you have a pressure cooker, water in this, and then you suddenly open the lid, don't do that, you will see that immediately start bubbling. Okay, because it has become now, its pressure is reduced. Same thing. So it's actually the picture, I'll just give it here. So this is a chamber, superheated liquid. Liquid is kept inside, and it is superheated, and suddenly when the particle is going, then you reduce the pressure. Like you just take out the lid of your pressure cooker. You reduce the pressure. Then wherever the particles are going, along that they will form small bubble. Okay? And then you have a camera in front, you take a picture, and you get this beautiful picture. Okay? So now, once you have the picture, you can analyze it, and find out what kind of tracks are those, what particle it is. So this is a different question. But so a particle, so you have kept this one, you keep it here, and then you can use it. Okay. Then there are spark chamber. As I said you, whenever the particles are going through a medium, it is ionizing. Let's say I have kept many copper plates. Alternate plates are at high voltage, positive and negative. Okay? So that means there is a high potential difference between these two plates, between these two plates, and so on. Now a particle is going. What it is doing? It is ionizing. Once you've been ionizing means you are creating a short circuit almost. Ionizing means you are creating a short circuit. That means there will be a spark suddenly at that point. There is a spark along this point, spark along this point. So when the particle is going like this, many such electrodes, it will just spark, and then you take a picture. And this is the pictures you can see, those tracks are going. They're just light and coming. And these spark chambers were used to discover the muon neutrino at CERN and at BNL, Brookhaven Laboratory, and many other experiments. So like that. Now, those type of chambers, where one problem was that they are slow. In the sense, say for example, take that one, bubble chamber. A particle is going, at the same time, there is this piston which has to be pushed down, reduce the pressure. That is a mechanical method. Any mechanical process is a slow process. So that means once you've done that, you have to wait. For the next take picture, you have to again push the pressure, and then only you can take the picture. So these are slow devices. So once we had started building, accelerator where millions of particles are being produced all the time, these detectors became obsolete because they are not, up to the mark. So you have to invent newer kind of detector. And then these detectors are all electronics detector. These devices are what you call multi-wire proportional chamber. What is there? These are wires, something like gold tungsten wire, 100 micron thickness, and then they are separated between, there are many of them side by side, and then you are separated by then two cathode planes. So this anode wire is kept at say some positive voltage, few thousand volts, and this is at ground. So then there will be a potential difference between these. Now a charged particle is going. It is creating electron-ion pair in that gas, okay, argon gas or something. And once that electron, all those electrons immediately start moving toward the central wire because that is at a positive voltage, okay? They will be attracted. And once it goes close to the wire, the field there is so high because they will start multiplying from 1 electron to 2 electron, 2 electron to 4 electron, 4 to 8 and so on. So you will multiply the signal and the wire will give a pulse, okay? And that pulse is detected, amplify in an amplifier, and then through that one. And if you put many such stack, one multi-wire proportional chamber above another, so you can trace the whole track, and then you will start seeing those kind of tracks and then find them. And you can see this, he has put one such chamber here, Chalpok. In fact, if you can make them, you can make them a huge volume using those wires, okay? And then whenever a charged particle is going, you can trace them. This is actually thousands of particles are created at the center where the collision taking place. They are all going, and they are all individually, we can get pulses and plot them in a computer and get the picture, okay? This is how we do. Not all the time you have to have that kind of detector. Even this is a liquid detector. This is a liquid argon. Liquid argon is same thing. In the liquid argon, particles comes. Actually, this is a neutrino. A neutrino is a neutral particle. That's why there is no trace of track anywhere. Suddenly, at this point, neutrino comes and it interacts and produces new particles. And those particles are moving inside, and then again the charge is collected and you get their picture. Okay, this is the detector is filled with liquid argon, and then you do this. This is a detector. Actually, if you have gone to this exhibition there in the INO stall, you will see there is in front of them there is a model where cosmic rays are going, and they are getting this LEDs are getting glowed. So this is exactly the same detector we are developing in India for this INO experiment. This is a glass plates, and this is a glass plate. These two glass plates, these are the window pan, whatever you use, 2 millimeter thick glass plates, separated by 2 millimeter gap. Okay? And you coat the outer surface of those glass plates by graphite coating. Then apply high voltage between these two glass plates. Of course, this is sealed, and inside that there is a gas. And then you have this. So the graphite coating is basically to apply high voltage. Okay? Otherwise, you cannot apply high voltage to glass plate. And then on the top of that, you have these pickup strips. Okay? In this way and this way. I think you have a picture here. You can.
Later we can have a look.
Yeah, you can have there. Maybe you can. This. Show me this one. Yeah. Here. So this is. Give me that glass. No, RPC. Yeah. Is that one? Oh no, that one also will do, no? Yeah.
Glass.
Glass only, no? Oh, sorry. Okay, no. Yeah. So this is actually the RPC. You see, there are two glass plates, graphite coating, black. You can see. Now, a gas is going inside, gas is coming out. I apply high voltage through this one, and then I put this pickup strip on top of that, and leave it. Now a particle going through that. When it is going, it is creating ionization. And because I have applied a very high voltage between the glass plates, these electrons will multiply. And then this fellow will give a pickup pulse in this strip. If it's going through this point, the corresponding strip will get a pulse. If it's going through here, this corresponding strip will get here. And if I put a strip like this here, in this direction, the strips are and opposite 90 degree, then I can get both x and y coordinate of that particle, and it will be detected. So this is exactly the. In fact, of course, this one is 10 centimeter by 10 centimeter. But what we are making is 2 meter by 2 meter size such detector, huge particle detector. And we need for the ion experiment 30,000 those particle detectors, stack one above other, and the particles will go and they will track them. Okay? That's what is happening. These are called scintillators. It is not that particles are going through all the time, they only create ionization. They also create excitation of the atoms. Okay? So if we excite an atom, then the atoms will come back to the ground state and it will emit photon, light. And sometimes that light can be collected by some light detector, and then you will be able to know the particle detector. So this is kind of scintillators. Here, for example, this medium. Okay? Good. So here you can see this one. So here, see each of them, you will see they are all scintillators, block. And then light is getting collected by those fibers from inside, and they will guide outside, and then we will put a light detector here. This one is similar. This is a scintillator block, and when the light is the particle is going through that, it will producing light. I am putting the fibers around it, and then I will put a photo detector here. The light will be collected, and then you put stack one above other. You will be able to see the tracks, and so on. There are many kinds of detectors you can make like this. Okay. So this is, and then okay, let me just, even you can you can even use water just as a particle detector. You know, if you have a clean, transparent water, and sometimes a particle can come and produce, say for example, this is a neutrino and produce an electron. This is electron. And this particle, a electron, when it moves through the water, it produces light. You don't see that, but it produces. And this is called Cherenkov light. And they produce light in a ring. So like a cone. A particle is going and along a cone. A particle is going along a cone. It produces that light. And this is a detector in Japan where they have a water. And you can see this guy is just going in a boat in a water and fixing those photomultipliers. Huge. How big it is? Something like 50 meters in diameter and 70 meters in height. And the walls of that huge cylindrical swimming pool is filled with particle detectors. These are called photomultipliers. They are just watching, looking towards the water, waiting for light to fall in it, and they will collect the light. There are 10,000 of, actually 11,000 of those photomultipliers are there in this experiment. And whenever suddenly a particle will go, some of those photomultipliers will get light, and from there you can find out the direction. You can put those photomultipliers in the bottom of the sea. Just you want to make a huge detector, a kilometer cube detector. Sometimes for detecting particles, we have to make big detectors. Big means really big. a kilometer cube. So how can you do that? So you put these are photomultipliers at the bottom of the sea, anchored at the bottom of the sea in a string, just looking down, each of them photomultiplier in some string. And this is a buoy which is keeping it floating, okay? Allow it to float straight. Like that, you just put a large area, you covered many such strings of photomultipliers. That's it, your detector. And of course, you have to collect the signal from each of them, all the wires, and then bring it to the surface and put it in a control room and then detect it. But this is the whole idea. And you can make just plain water, use detector. Now, so all these things, let's go back to my original thing. How do we have collision? So let's say a proton comes from this way and a proton coming this way, they colliding at this point. When it collides, they produce new particles, like this, two particles. As I told you, like Higgs boson or top quark or something, they are not stable. They quickly decay to other particles, okay? So for example, this particle may have decayed into some other particles, two sets of particles. This particle may decay into some other particle, maybe two photons, and so on. What you do, you have to trace those tracks, okay? You have to trace those tracks for some distance in a magnetic field. Then you can measure their momentum, you can measure their energy, and then finally find out the total momentum of this event. And if you can find out the total momentum of these particles, and then add them, and this is the mass square of these particles, that is this, you get the mass of this particle back, okay? So this is how we find the particle mass. And so let me just move out of this one. So let us say you are doing an experiment. So you have this one, you have particles, and then you got this picture. Now in this picture, you are not interested in all those events, all those tracks, because most of them are background. You only interested some of those very high momentum track, high energy track. So what you do, once you put a magnetic field, all those, you are saying many of them are getting curled, those are low energy track, because they get bent more and more if their energy is low in a magnetic field. So from their curvature in a computer, you can easily find out their momentum and throw them out. You don't say, I don't want into picture, I want to clean my picture. So you go that one and you clean it up, and then it will come up, only those tracks which are very high energetic tracks will remain. And then some of them you may probably see the energetic one, if they add there and measure the mass of the original particle and maybe plot as a function of mass, and then you will see some extra event at some mass, and in this case in 125 GeV or so. So that means something else is happening. These are all background events, okay? They are just following some standard pattern. But suddenly there is a bump, there is an excess of event at some particular mass above background. And if you've seen that, then you have seen something new. And that is how the Higgs was discovered, okay? This is done. So this is an accelerator, okay? You have to find the accelerator. But not all particles you detect in an accelerator. For example, you will be surprised to know that all the particle story that I told you so far is only telling about only 4% of the universe matter energy. Only 4% of the matter of our universe, or total mass energy of the universe, is in the form of electron, proton, neutron, quarks, and so on. That's it. What about the rest? A large fraction, something like 25%, is also in the form of some other particle, but they are called dark matter, because they do not interact like the ordinary matter. See, the ordinary matter, a proton, electron, etc., is going through your medium, it is ionizing, because it is interacting through electromagnetic interaction. But those particles, they don't do any of those. So if it doesn't do all those things, how do I detect it? So there has to be a different method to detect those dark matter. So one method we thought is that, well, if the particle has a mass, it comes, and I have a nucleus here, I have kept some matter. If it hits that matter, then sometimes it will hit a nucleus, and the nucleus will get displaced, okay? Once the nucleus gets displaced, it will start moving. Then that nucleus will create ionization, or it create light, and so on. So for example, in this experiment, we do the same thing. Here is a dark matter, it comes and hits the nucleus, and the nucleus may be moved, okay, little bit. And that will give us some light or some ionization, and we can detect that. So this kind of detector, you don't have to go to an accelerator. You have to just build the detector and go to a nice underground place. Why underground? Because this signal is very, very tiny signal. If you do it in the surface, there are so many other cosmic rays are coming. They are also doing the same thing. So you will not be able to distinguish from ordinary particle from a dark matter signal. But if you go deep underground, all those ordinary particles we know, because they are interacting with matter. They are losing energy. So if you go deep underground, none of them will reach there. That's why we want to do underground experiment, because all these background events can be filtered out. And there, you just put this detector and then wait for the signal to come. And if you see that, and people are doing this experiment for last 20 years, they have not yet seen it, but we have to see it, because we know there are 25% of the matter is there in the form of dark matter. So this kind of experiment you can do even in India, where there is no other accelerator. Okay? You don't have to go to a CERN all the time or Geneva, and you can do such experiment in the country. And this is finally what we wanted to do with those particle detectors, that RPC that we are developing. We want to build a huge detector, 50 kiloton detector. Okay? This is the size of the detector, and there are 150 layers of those RPC and stacked in between iron plates. The iron plates are getting magnetized by this magnet. These are the coil going through these iron plates, okay, and all around, loop around. So all the iron plates are magnetized. So this is how it is developed. One layer of iron plate, and then those RPC. Each one is 2 meter by 2 meter. Those same that kept there, but only big. And 2 meter by 2 meter. Stack them, put next layer of iron plates, then another layers of. So the sandwich of these iron plates and these RPCs. Now why this is there? So let us say we want to detect neutrino. What do the neutrino come? A neutrino come inside our detector and it will produce a muon. If it is a neutrino, it will produce a mu minus. If it is an anti-neutrino, it will produce a mu plus. Mu plus and mu minus are just opposite. How do I know whether it is a mu plus or mu minus? Because in the magnetic field, they will bend in opposite direction. So I will trace their track, and from their curvature, I will know whether it is a neutrino event or an anti-neutrino event. And by studying those events, we will be able to find out certain properties of these neutrinos, which is very important, and it is not known yet for scientifically. And this is one of the most fundamental questions that the whole world community of particle physics is asking. So we could have been part of that big thing, and we have already done everything, but we can't make it because there are some activists and politicians. They are just misleading the public, telling that we don't want to do this kind of experiment. We want to go and make neutrino bomb. That's what we are, So this experiment has to be done underground. So we have identified a site in south in the south in Tamil Nadu, but in the rural area, basically the farmer lives there. So politicians are going and telling them that all this some lies. We have not been able to clear their mind yet. So this is stuck, this project. But if it is there, our students from this country itself, they don't have to go to CERN. They can build such experiment and do this experiment here itself. Okay. So that's something I wanted to tell you.